So now everything that you have learned about electron configuration, we're going to take that and boil it down to the pieces that are the most important. When you have atoms that are going to interact with each other, which is really what chemistry is all about, what you have to realize is that if an atom, if I think of the whole thing as a ball or a sphere, if I have two atoms that are going to interact with each other, as I bring them closer and closer together, the parts that are going to interact first are going to be the parts that are on the outside. They're not going to be the electrons that are buried really down in the lower energy levels, really close to the nucleus. They're going to be in the energy levels that are the furthest out from the center of the atom. So the highest energy levels that contain electrons are going to be the ones that interact with one another. Like I said, if I bring the two balls together, it's the outsides that touch first. So the electrons in the atoms that are in the highest energy levels are going to be the ones that interact with each other. So that's where I start talking about valence electrons. And he defines this for you. This definition probably looks a little bit different because I want to be really specific as to which electrons we're talking about. So the valence electrons are only the electrons in the s orbital and the p orbital that are in the highest energy level for that atom. Now you'll remember that on the periodic table, the s block are the two columns on the left-hand side, and the p block is the 6 columns on the right-hand side. So those are the electrons that we're looking at when we're talking about valence electrons, and we're only looking at the ones in the highest energy levels for the atom. Now, in your book, on page 110, he actually gives you what are called Lewis dot structures for the for the third row of the periodic table. What I have on the board behind me is the atoms in the second row for the periodic table. So we're going to look at the valence electrons here and compare that with what he has in the book. So if you look at lithium, and again, have your periodic table in front of you. If you look at lithium, you know that that's in the s block, and so that's the outermost electrons are going to be 2s1. So there's just one electron in the second energy level, and I'm going to represent that by writing the symbol for the element and putting one dot next to it to represent one valence electron. Now, when you draw dot structures, it doesn't make any difference which side you put it on. Whether you put it on, you can put it on the right, you can put it on the top, you can put it on the left, you can put it on the bottom. Any one of those places is fine. And in fact, as we get a little further into this, we'll start shifting them around on different sides of the symbol just to make life a little bit easier for us. So where you put it doesn't matter. What matters is how many you put down. When I look at beryllium, it's second in the row. So if you remember from the electron configuration, that's going to be 2s2. So I have two valence electrons. I normally don't start pairing them up until I get one on each side, and then I start pairing them up. Okay, so beryllium has 2. You get over to boron, which is in the p block. So that's 2s2, 2p1. So my 2s electrons are on two sides, and the p electron is on the third. Carbon, 2s2, 2p2. Again, if you're looking at your periodic table, 2s2, carbon's in the second column in the p block, so there's 2p electrons. So I've got my 2s electrons and my 2p electrons. Now I've got an electron on each side, and so when I get to nitrogen, which is going to have yet another p electron, now's where I'm going to start pairing them up. So nitrogen, and another way to think about this is to count how many over you have in just your s and your p block. So nitrogen is going to be 1, 2, 3, 4, 5 valence electrons. So it's going to be 1, 2, 3, 4, 5. Now you see I've got one pair and 3 singles. In oxygen will have yet another p electron. So I'm going to have 6 total electrons, 2 pairs and 2 singles. When I get to fluorine, there are 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. So I have 3 pairs and a single. And then finally neon on the far right hand side, 2s2, 2p6. So that's going to give me 2 s electrons, and then 1, 2, 3, 4, 5, 6 p electrons for a total of 8 valence electrons. Now, if you have your book open to page 110, he gives you the elements in the 3rd row of the periodic table. And if you notice, the elements that he gives you there match exactly what the element is above it. So if I look at the first column on the periodic table, lithium, sodium, and then potassium, rubidium, cesium, all of those will have an identical dot structure. They're all in the 1s1 or in the s1 column, so they just have 1 valence electron. Everything under beryllium is in the 2s or in the s2 column, and so they all have 2 valence electrons. Everything under boron has 3. Everything under carbon has 4. And so what that means is that as long as you've got, the first row figured out, everything after that, as my son likes to say, is gravy. Meaning everything after that's easy because they all match up in the column underneath. Everything underneath nitrogen, the dot structure looks exactly like this. Now, I want to tell you about a rule that Dr. Weil did not mention in the book, but I do expect you to know this rule, so you might want to grab a piece of paper and jot this down. It's called the octet rule. If you're familiar with the word octet, octet means a group of 8. And so the octet rule means that atoms want, if an atom could want something, it's obviously not alive, but if it was alive, atoms want 8 electrons around themselves in order to be happy and to look like a noble gas. Everything in the far right-hand column has 8 electrons around it. So everything over here, neon, argon, krypton, xenon, and radon, all of those have 8 valence electrons around them. You can see it looks like it's full. And so when you get 8 electrons, this atom is very, very stable. It doesn't like to change. It doesn't like to react with anything else. And so it's called a noble gas. And what I remember that is that if you're of nobility, sometimes the nobility doesn't like to interact with the common folk. But everybody thinks it would be really cool to be nobility, to be the king, to be the queen, to be the princes and the dukes and the duchesses. And so everybody wants to be like the nobility. In the element world, all of the elements want to be like the noble gases. And so in order to be happy, they want to have 8 electrons around themselves also. So for fluorine, he is 1 electron short. So if he could gain another electron, he would look like neon. His electron configuration would look like neon, and he would be happy. So if he's happy, he's stable. He's not going to interact a whole lot. But the thing is, he now has 1 more electron than he usually does. And if you remember, normally in an atom, the number of electrons and the number of protons balance. He now has an extra electron. Electrons have a negative charge, so he's got 1 more negative charge than he did before. So now the total charge on this is a -1. And now he's no longer called an atom. Now he's called an ion because he has a charge. Whenever an atom gets a negative charge on it, we add an IDE ending to it, and we call this, instead of fluorine, we call it a fluoride ion. Let's look at oxygen. Oxygen has 6. It wants to look like neon, which has 8. So if oxygen can gain 2 more electrons, it will look like neon, and it will be happy because it looks like a noble gas. But it's gained 2 electrons in order to do that. It now has 2 more electrons than it does protons. So that's going to give it a -2 charge. And for some reason, normally we write the number and then the charge. I'm not sure why. That's just the way chemists tend to do it. And so this was an oxygen atom. it has now become an oxide ion. Carrying this one step further, nitrogen. Nitrogen has 5. It wants to look like neon, so in order to do that, it's going to have to gain how many electrons? Right, it's going to have to gain 1, 2, 3 in order to have a total of 8. This was a nitrogen atom. Now it is an ion. What would the charge on it be? It's added 8 electrons, or I'm sorry, it's added 3 electrons for a total of 8 valence electrons. If it's added 3 electrons from what it had, it's now going to have a -3 charge, and I'm going to call this a nitride ion. Now what you may be thinking is, okay, so when I get to lithium then it wants to gain 7 electrons. Well, you could think about it that way, but in reality, it would be a whole lot easier just to lose an electron than it would be to gain 7. So that's what lithium does on this side. It's just gonna take this electron and it's gonna get rid of it. So then if you think about that, lithium now looks like the noble gas above it, which would be helium. But we don't put anything around it because it has lost an electron. If I've lost an electron over what I had before, that means I have 1 more proton than I do electrons. So this is going to have a positive charge, and I don't change the ending on this. Now it's just called a lithium ion, and I still call it lithium, but I put the word ion on with it. Beryllium, it's easier to lose 2 electrons than it would be to gain 6. So beryllium is going to lose both of those, which is going to give it a +2 charge. And so I'm going to have a beryllium ion. And boron's a little weird. Carbon especially is a little odd. Aluminum underneath boron, if I look at aluminum has 3 electrons, and so it's going to lose 3 electrons to become an aluminum ion. So boron is kind of in a special case. We'll talk about why a little bit later. Carbon either has to gain 4 or it has to lose 4. It's kind of, well, it's 4 of one and 4 of another. So which direction it goes depends on what element it's going to combine with. And again, we'll talk more about that as we really start talking about making compounds. So what you need to realize is that this octet rule is going to be obeyed by a lot of atoms because what they want is 8 electrons around themselves. So they're going to gain electrons or lose electrons in order to do that. And when they gain or lose electrons, then they are called ions.